6.7 is the fundamental theorem of calculus and definite integrals. Okay, so just kind of a reminder here, fundamental theorem of calculus allows us to evaluate definite integrals when we can find an antiderivative. If f of x is continuous on the closed interval from a to b, and g of x is an antiderivative of f of x, then we have the integral from a to b of f of x dx equals g of b minus g of a. Okay, so we're going to take a look at the evaluation part of fundamental theorem of calculus. So these are just reminders again. First one, the g of prime of x is equal to f of x. That's what we first talked about with fundamental theorem. And then what that really means is that if I do g prime of x, I can evaluate that as g of b minus g of a. Okay, and then just remember that the antiderivative of g prime of x is just g of x. And that concept is going to come in a lot over these problems today. Okay, the antiderivative of g prime of x is just g of x. All right, so for our first example, we're evaluating the integral from 0 to pi over 2 of cosine of t dt. Okay, so when we apply this, we just need to remember that one of the key parts to this is that the antiderivative of cosine of t is sine of t. Okay, so that's our key here, because once we remember that the antiderivative of cosine of t is sine t, then we can go right into that difference part of the fundamental theorem. So what we're really saying here is from 0 to pi over 2 cosine of t dt is equivalent to saying sine of pi over 2 minus sine of 0, which is just going to come about to be equivalent to 1. Okay, so again, we're saying that the one way that we can use fundamental theorem here is to actually use the antiderivative of this cosine of t, which is sine, and then do sine of your upper limit minus the sine of your lower limit. Okay. All right. Same idea for this one, except this one is even a little bit easier in my opinion because you don't have to remember what the antiderivative of cosine of t is. So again, we are looking for the antiderivative of 3x squared. Okay, and that's just going to be x to the third. So what this ends up meaning is we have the integral from 1 to 4, 3x squared dx is going to be equivalent to x to the third being evaluated at 4 and 1. So upper limit is 4 to the third minus our lower limit, which is 1 to the third. And then we would just simplify that, which comes out to 63. Okay, so again, you're going to find the antiderivative of your function and then evaluate that antiderivative at each of your limits, your upper limit minus your lower limit. All right, so this is one that we actually saw in that first lesson that I did with you guys, which gives us this table. Okay, so we have this function of g of x from 0 to x of 2t dt. And we had filled in this table by creating all those triangles under the line and adding them all up. I'm not adding them all up, but filling in our table here. Okay, well, we can use this same idea of our fundamental theorem and say, okay, well, we've got g of x is the integral from 0 to x 2t dt. And really what that's equivalent to is the antiderivative, which is going to be t squared, and then evaluating t squared at x and 0. Okay, so when I find the antiderivative of 2t, it's going to be t squared. And then I'm using that t squared and evaluating it at x and 0. So that means that this is going to be equivalent to x squared minus 0 squared, which is x squared. And then you can see here also the connection between that and this table that we did in that 6.2 lesson. Okay, x squared gives us all of those values. Okay, you can also apply the first part of fundamental theorem, which says that g prime of x equals f of x. If we find the derivative of x squared, it's just 2x. Okay, which brings us right back to all the stuff over here. Okay. Okay, hopefully I'm not going through this too quickly. The plus side, you guys don't have to, you can pause it whenever you need to, or go back and watch it whenever you need to. All right, so now we have a graphical example. Okay, so you've got the graph of y equals f of x, and you're looking for the integral from 1 to 3 of f of prime x, f prime of x dx. Okay, um, so once again, we're talking about this idea of an antiderivative. Well, if you think about what we have right here with this f prime x, the antiderivative of f prime of x is just f of x. Okay, and we're given the graph of y equals f of x. Okay, so when we're looking for where the antiderivative of f prime of x is just f of x, and that is our graph. You know what? I just realized this one doesn't have the graph in it. All right, give me 1 second here. All right, I'm going to go back and add that problem at the end. I just realized that the graph isn't actually on there. So we'll talk about that one at the end, and I might add that in there. Okay, missing an image there. That's not going to be super helpful for you. Okay, and then our next example is one that is in the form of a table. Okay, so we're given that the table gives you the values of a function f and its derivative at selected values of x. Okay, so we've got x, f of x, f prime of x. If f prime is continuous on the interval from -4 to 1, sorry, -4 to -1, what is the value of the integral of -4 to -1 f prime of x dx? Okay, so we're looking at our table, and again, if we're looking for the antiderivative of f prime of x, which is what we're looking at right here, the antiderivative of f prime of x is just f of x, and we have the values for f of x in our table. So what we're doing is evaluating, and this is another, it's like a new format for showing that you are substituting in values. Okay, so we're evaluating f of x from -4 to -1. So it's just kind of a different notation to show that you're substituting in and evaluating that. Okay, so that gives us f of -1 minus f of -4. Well, if we look on our table, I'm looking under the function f of x. When I look at -1, the value there is -1.5 minus the value at -4, which is 0.75. Okay, and that gives us a value of -2.25, which would be B. Now, a couple of things to watch out for as far as common errors here. The first one would be forgetting to use your antiderivative and just using f prime of x and evaluating that. Okay, so that would be like 1.5 minus -3. Another potential common error would be to subtract them in the wrong order. Remember that you're doing your upper limit minus your lower limit. Okay, and then we've got this new notation that we have right here. All right, for this next one, g of x is an antiderivative for f of x. G of 2 equals -7. We're looking for g of 4. Okay, so we're saying that g of x is an antiderivative for f of x, which really means that, which really means that g prime of x is equal to f of x, because we're saying that g of x is the antiderivative. Okay, so if I were to take the derivative of g prime of x, I would get f of x. And so what I'm doing here is I'm actually looking for the limit, sorry, the integral from 2 to 4, okay, f of t, sorry, f of t dt. We already set up here in the right above here that f of t is equivalent to g prime of t. So really that's equivalent to the integral of 2 to 4 g prime of t dt. Well, in my given information, I'm given what g of 4 is. Okay, so I'm going to evaluate this using that fundamental theorem and say that I'm looking for the antiderivative of g prime, which is just going to be g, and I'm going to evaluate it at each of my limits. Okay, so my upper limit is going to be g of 4 minus g of 2. Okay, now we already know what g of 4 is. Okay, that's equivalent to negative, I'm sorry, we don't know what g of 4 is. Sorry, we know what g of 2 is, and that is negative 7. Okay, so just to kind of write this out a little bit more clearly, we've got the integral from 2 to 4 f of t dt equals g of 4 minus g of 2. Well, I can move that g of 2 over. So now I have, I'm going to add the negative, or I'm going to add the negative and a negative make a positive. So when I move that over to the other side, it's going to end up giving me a negative 7 plus the integral from 2 to 4 f of t dt, and that's going to equal what I had left on the other side, which is g of 4. And if you notice, that would be choice D here. Okay. They wrote it in a slightly different format, and this is what we talked about yesterday, how you can take the integral of those two parts and kind of pull that out to the front. Okay, so that's what they did there. That one is a little bit more complicated. I will say that. Okay. And now we have this messy looking thing. So this one is the derivative of a function h is given there with all that stuff. We're looking for the integral from 2 to 3 of that mess. Okay, so it's saying that the derivative of a function is h, which means the derivative or the antiderivative would be h prime. Okay, so the derivative of the I'm sorry, let me rephrase that. The derivative of the function is h, so that means that can be represented as h prime. Okay, the derivative of h is h prime, and that is given to us as e to the 2t times cosine of e to the 2t. Okay, so again, derivative of h prime is the derivative. Okay, so we're going to look for, they're asking us what is the integral from 2 to 3 of all of that. So we have the integral from 2 to 3 of e to the 2t times cosine e to the 2t. And now we're going to look at, well, what is the antiderivative of this? Okay, and we know that the antiderivative of h prime is just h. Okay, so this is what's given to us as this whole thing is h prime, okay, from up here. So we're looking for the antiderivative of h prime. That's going to be h. And so I can just do my fundamental theorem, which says h of 3 minus h of 2. And that happens to be given to us here in choice C. All right, next one. Again, I know this is a lot of stuff, but on the plus side, this is recorded, so you guys can stop, pause, record, take a screenshot, whatever it is you need to do. Probably easier to do this one this way. All right, so a couple of reminders here for this one. The integral of a rate of change gives the net change. sorry, I have a little typo here. G prime of x is the rate of change of G from A to B is the change in G from A to B. Okay, G can be any function with a continuous rate of change, and G prime of x could model lots of different rates of change. So now we're going to look at a couple examples for integrating a rate of change. All right, so for this one, we've got this whole thing. I'm not going to read that to you. You guys know how to read. But basically, we're looking at the temperature in water increasing, and it's over a span of 30 minutes. Okay, now this table happens to represent the time from 0 to 20 minutes. Okay, and the values of W of t at selected times for the first 20 minutes is given in the table. So we're going to use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. Now, the key thing here is going to be at the end, using those correct limits to make sure that you can interpret the meaning of that result that you get. Okay, because when you do this for an open, for a free response for the AP test, you need to make sure that in order to get the full credit, you're going to be using the correct units and actually interpreting what that meaning is. Okay, so once again, we are given the limit from 0 to 20 of W prime t dt. Fundamental theorem again says that if we do the antiderivative of W prime of t, we just end up with W of t. And that happens to be what we are given in the table. So what we can do is write this as integral from 0 to 20 W prime of t dt is equivalent to the antiderivative of W prime, which is just W, and then I am evaluating that at each of those limits. So that's going to be W of 20, which is 71, minus W of 0, which is 55. Okay, I probably should have put that here. So W of 20 minus W of 0, and that gives us 16. Now, once again, if you were to just write 16 here, you're probably not going to get full credit for this because you need to make sure that you are using the correct units and interpreting what that meaning is. So the best way to describe that is that you are, the water is increasing at a rate of 16 degrees from the interval t equals 0 to t equals 20. Okay, so 16 degrees over 20 minutes. Okay, so 16 degrees per 20 minutes. Okay. All right. Now we're using, what happened to my other questions here? Oh, okay. All right, so now we're going to switch gears a little bit. And hang on a second. Okay, so I'm going to pick up where I left off. Sorry this is so choppy. I'm having some major recording issues with Screencastify today. So I'm going to pick up where I left off with our with the problem that was asking how the water is increasing in temperature. So we talked about using the table. Okay, so the table goes from 0 to 20. When we look at the second problem, okay, this is picking up where we left off before, and we are talking about what happens on the interval from 20 to 25. Okay, the function W that models that water temperature has a first derivative given by W prime of t, and it's all of that. Okay, so based on the model, what is the temperature at the time of t equals 25? So we're talking about how the first derivative is given to us by W prime of t. So again, keep in mind that what that fundamental theorem says is that we can use the antiderivative of W prime of t, which is just W, and we can identify what our value is at that interval. So we're looking for we're going to start with finding out what that integral is. Okay, so the integral from 20 to 25 of W prime of t. And our antiderivative I'm sorry, just our integral. Okay, so we're going to plug this into our calculator. So integral from 20 to 25 of 0.4 square root of t times cosine 0.06 t. Okay, and you're going to actually plug that right into your calculator, and that's going to give you the water temperature change from 20 to 25 only. Okay, we're looking for what the water temperature is at 25 minutes. Well, in order to actually know what it is at 25 minutes, we need to take into account what it was. Let's take a quick look back here at the table, what it was at W of 20. Okay, so when W at 20 minutes, it was 71 degrees. And then we're adding on that increase from the interval from 20 to 25, which comes out to, when you plug this into your calculator, you get 2.043, and then you would add those values together to get your actual water temperature at time equals 25 minutes. Okay. All right. Then we have this next one, which is talking about fish that are entering and leaving a lake at a particular rate that is given by these two functions. Okay, so fish enter a lake modeled by E of t. They leave the lake at a function that is L of t. Okay, both of them are measured in fish per hour, and t is measured in the hours since midnight. So we are looking to find how many fish enter the lake over a 5-hour period from midnight to 5 a.m. Okay, so from when t equals 0 to t equals 5. And we're going to give our answer in the nearest whole number because we're talking about fish. So decimals aren't exactly accurate for the number of fish. So what we're actually looking for here is this first part is asking us how many fish are entering. So that means we're going to use our E of t function. So we are looking for the integral from 0 to 5 of 20 plus 15 sine pi t over 6, and you are going to plug that right into your calculator. Okay, and what we get is 153.457, and again, we're just going to run that to approximately 153 fish. Okay. Now, the second part of this question is asking about the number of fish that are leaving per hour, but it's adding in another element to this, and that's asking for the average number of fish. Okay, up here we're just saying how many fish are entering. For part B, we're saying what's the average number of fish. We can still do it in basically very much the same way. We're going to still use our integral from 0 to 5 because that's still our time frame. We're going to use the L of t function this time because we're talking about leaving. And then for average, so when we did the integral for the number of fish entering, we were able to get the total number of fish in that period, which is 153. If we're talking about the average number of fish that are leaving, we're still going to use that integral from 0 to 5, which will give us our total number of fish. But to find the average, I can take that number and divide it by 5. Okay, so get it as the number of fish that are leaving over the 5-hour period per hour. Okay, so this is going to look like the integral from 0 to 5 of the one that's leaving. So 4 plus 2 to the 0.1 t squared. And then the one thing that's going to change about this one, though, is that we're actually going to take whatever we get as our total, and we're going to multiply that by 1/5 or divide by 5 to get our average. Okay, so once again, plug that right into your calculator, and this time it's just asking for an average, it's not asking us to round, so you should get 6.059, okay, fish per hour. Okay. That is that. Okay, so this is the problem that we were missing, or that I was missing with the graph. So I'm just going to try and throw this in there at the end. Okay, so this should make a little bit more sense with the graph now. The graph of y equals f of x is given. What is the integral from 1 to 3 of f prime of x dx? So we said before that when we're using this fundamental theorem, it means that you're looking for the antiderivative of your function. Okay. goodness. So that means we're looking for the antiderivative of f prime of x, which is just going to be f of x. And that's the graph that we're given. Okay, this graph that we're given is y equals f of x. So when we're looking for how to evaluate at our limits, we're looking for f of 3 minus f of 1. And when we do that, we're going to look at our graph and actually figure out what our values are based off of that. So look for, on your graph, you're going to look for f of 3, which happens to be up here. So that gives us 6 minus f of 1, which is right here, and that's 2, which gives us 4. And I had told you guys this in a following problem, but since I'm going back to add this in, remember that you can also use this notation of f of x from 1 to 3, and that means that you're evaluating the function of f of x at 1 and 3. So that would be f of 3 minus f of 1. So it's just kind of this new notation here that we're using for evaluating.